All right, so it started recording. So let me start sharing my screen. All right, so I haven't seen you guys in a week. Well, I haven't seen you guys in like a month, but we haven't met in about a week. So what I want to do today is just do a quick, oops, let me do this. I'm going to turn off my Outlook so we don't have to keep getting that annoying noise. All right, and now we're back. All right, so you guys still can see the title screen, right? I'll take silence as a yes. All right.
No,
So,
I can't see
oh, you
it.
can't see. Okay, so that's what I'm saying. I think it messed up the share when I did that. All right, so now you should be able to see the title screen.
Yep.
All right, great. All right, so I haven't seen anyone in like a week. So the plan I want to do is just to kind of like a quick bird's eye view of the topics that we covered last Wednesday. And then what we'll do is we'll start moving into the new material. So why don't we get started? So this whole chapter on acids and bases, right? And we started with our more simple definition of what an acid and a base are, right? So we had our Arrhenius acid, and it was any substance when added to water, it's going to form H plus or hydrogen ions. And then anything that's going to be classified as Arrhenius base will be a substance that when dissolved into water is going to produce hydroxide, right? And we said this is not the best definition, but it's a good starting definition. The reason for that, some of the drawbacks, like having a H plus, right? We know that protons are unstable when they're not bound to anything. So we know that it's actually going to be in the form of hydronium. And so we increased our sophistication of our definition to Bronsted-Lowry acids and bases. And in this case, right, when we're looking at a Bronsted-Lowry acid, we're going to have a proton donor, right? So again, that H plus. And then for a Bronsted-Lowry base, we're going to have a proton acceptor. So you have one molecule that has a proton that's donatable. That's going to be our acid. And it will donate it to a molecule that has space on it to accept that proton. That's going to be our base. So just a little bit of a heads up. I don't know if I mentioned it last time. Usually what allows a base to accept a proton is a lone pair somewhere on the molecule. And we'll come back to that later at the very end of the chapter, because this is going to lead us to our final definition of acids and bases, which are Lewis acids and bases. But for now, we're sticking with proton donor and proton acceptor. So you can't have a donor without something to accept it. And so that led us to conjugate acid-base pairs, right? What we did last week, I'll just do a quick example again, right? If we're looking for pairs, we took an example, something like, say, HCl, and I'm going to leave out states of matter just for clarity, right? And we said we could react it, say, with ammonia. Well, if this is going to be my Bronsted-Lowry acid, that proton gets donated to the base. So I have my Bronsted-Lowry acid and a Bronsted-Lowry base. If I track and predict my products, well, I can see that the HCl lost a proton. And that was a positive charge, so I'm left with the chloride. And then that ammonia, the NH3, gained that NH plus. And so there's my additional H, and then the charge that came along with it. When I'm looking at Bronsted-Lowry acid-base pairs, right, we're looking for something kind of structurally similar. So we have our Bronsted-Lowry acid. Well, what's structurally similar to that? It's the chloride. And it was an acid on the left-hand side of the reaction. That means by definition, that has to be the conjugate base. And we can do the same thing with the ammonia. Structurally almost identical to the ammonium, the NH4 plus, and then that will make that our conjugate acid in this case. And it actually doesn't get any more difficult than that. So once you've kind of mastered that, which maybe by now you have, you're in pretty good shape at identifying acid-base pairs. This led us into discussing, because one of the examples we did produced hydronium, And we said, this is actually, it's kind of foreshadowing. We're gonna do a lot today with this molecule, right? But this is going to be leading us into basically what our definition of acids are. And ultimately what it's going to do is help, it's gonna basically, the concentration of hydronium is what the pH scale is based upon. So this is kind of more of a summary slide, so I can skip through that, right? But it's basically what I went over in that hand-drawn slide. So once we did define what an acid and base are, then we started to define what do we mean by acid-base strengths. Why can I drink lemon juice and be fine, but I can't drink hydrochloric acid because I'm going to end up in the hospital, right? It deals with acid strength. And the two take-home messages about acid strength: strong acids nearly dissociate 100%. And so that's what this figure here is indicating, that if I start with some protonated acid, HA, if I let the reaction finish, HA is gone, and the only products I have are hydronium and the conjugate base. Usually when we write a strong acid reaction, right, if I take, say, HCl, which is a strong acid, I react that with water. We typically use a unidirectional arrow, and then you'll see me sometimes write 100% over the arrow, indicating it's a strong acid, and my two products would be chloride and hydronium. On the other hand, when we have a weak acid, what we want to think about is only partial dissociation. Usually, so when you think of like a strong acid's around 100% dissociation. Weak isn't like 70, it's like 10. Most weak acids are 10% dissociated or less. That's just a ballpark though. So, I mean, obviously everything's gonna be context dependent, but most are in that range of like lower than 10%. So how would I write that as a chemical reaction? Well, if I took something, I'm just use the generic HA. We're just gonna assume it's weak. I can also react that with water, just like I did with the HCl, but now what we're gonna do is we have our equilibrium arrow, because only some of it is gonna end up as hydronium and as the conjugate base, but other times it's gonna go back and reform that protonated acid. So only some of it is gonna end up as the H3O plus, and then the conjugate base. So far, so good. So keeping track of weak and strong acids is going to come up again. So if you do feel a little weak on it, we can tackle it right now, but we're also going to see this again a couple of times. All right. So what I had you do, or will have you do, right? All this slide is just, you know, kind of as a spattering of different chemicals that are strong acids or strong bases, right? So what I had you memorize, and it still says you do need to memorize those 4 strong acids. So you'll need to know their structures, and then you also need to know that they are strong acids. We also talked about strong bases, and I said for us, we're gonna ignore these strong bases. You're gonna see these in organic chemistry. So for our definition in 1102 is gonna be that metal hydroxide definition. So we know there's no element M, it just stands for any metal that's soluble in water. So like, you know, sodium hydroxide, potassium hydroxide, I think barium hydroxide, right? So it'd have to be a water-soluble metal hydroxide, and that will be our strong base. And then that's what we see here, hydroxide. I don't know if I mentioned this last time, but as you can see on the slide, the stronger the acid is, right? So these are all acids on the left-hand side. Oh, never mind, I messed something up. My bad, I was getting ahead of myself. So I'm gonna stop there, not to confuse people, but strong acids, I do need you to memorize those 4. And then for strong bases, note soluble metal hydroxides that produce hydroxide when they dissolve. So we also talked about water behaving as both an acid and a base. And I gave you 2 examples. They're generic, right? It's just saying if I have an acid donates a proton to water, the water's a base, and that's what that top example is. Or maybe I have water acting as an acid, and then it donates its H to that base. So that makes water both an acid and a base, and we said it was context dependent. But which is it then if I'm going to define it as an acid or base? We actually said it could be both, right? So it's been experimentally shown in pure water that water can react with itself. Depending on, you don't just look at say, okay, that one, he's going to be an acid or she's going to be a base. It's like, it doesn't work like that. It's when they collide, there's going to be, there's probably a lot of different variables that are happening, orientation, the speed at which they collide. One of them randomly is going to be an acid, the other is going to be a base, right? What happens in that case, right? Let me do this. Right, if we instead, follow it more with the cartoon example, right? We have two molecules of water. It's just showing that we have a hydrogen bond. That's what that that hashed mark is a hydrogen bond between the H and the other water. And we can see that that bond breaks and that forms hydroxide and leaves hydronium left over. So then I had you all write out an expression for this equilibrium, right? So we know our K, the definition hasn't changed. It's always products over reactants. I have my products here. I have my reactants here with the typo, right? But, and we caught this last week, we know water is not part of that K expression, right? Because we said, oops, pure solids and pure liquids do not go in K expression, right? We define that. There's other reasons why, but our definition that we're kind of keeping it simple is that technically their concentrations are their densities and those aren't going to change. So we omit them from the K expression. Oops, why did I skip 2? So we would end up technically our K expression is just the concentration of hydronium multiplied by the concentration of hydroxide. All right, so I'm getting to where my other class was. Remind me, so did we got about this far, right? I believe in terms of kind of our overview part of the lecture. This is where we stopped.
Yeah, I think so.
Did we get, yeah. So what I can do is I'll just pick up here because it's pretty much very close if we stopped here or close. So we can write out our K expression. Experimentally, it's been found that at 25 degrees Celsius, right, with pure water, the concentration of hydronium will be 1.0 times 10 to the negative 7th. So that had to have been found experimentally. Another bit of information we can pull out of this is that because this is pure water reacting with itself, that means only hydronium and hydroxide in pure water can only form in a 1-to-1 molar ratio. So that's why I have it written down here, even though the concentration of hydronium equals 1.0 times 10 to the negative 7th, hydroxide does as well. And that's going to be important. We'll see in a second. Well, why is it important? Because I can plug it into my K expression for water. And what I've shown on this slide, maybe I didn't mention it on the last specifically, is I've changed the subscript on it. And it's because this is a really important constant. It is used quite frequently, and that's why scientists have given it a special designation, and it's universally known that Kw is it means it's the equilibrium constant for water, or the autoionization constant might be something else you may hear. Another heads up, so when we're dealing with acids and bases, everything's going to be assumed to be at 25 degrees Celsius, because we know if we change that temperature, right, another way that we can express big K, the equilibrium constant, is the ratio between the rate constants of the forward and reverse reaction. And we know little k is dependent upon temperature through the Arrhenius equation. So we do know Kw is temperature dependent. So I'm going to say right now, all acid-base problems, unless otherwise specified, will be at 25 degrees C. Effectively, what that means is you can just always use this number of 1.0 times 10 to the negative 14th. to be Kw, right? And you get that by multiplying the concentration of hydronium by the concentration of hydroxide. So what other information can we pull out of this Kw expression, right? So on the top of the slide, I have basically just kind of smushed it back in together what Kw is and what its value is, right? What we can also do is rearrange this equation look like this, right? All I did was I basically divide both sides by hydroxide, so I'm now solving for the concentration of hydronium, right? We notice here that we have a constant in this expression, right? Constant's not going to change. That number has to stay the same. So we remember that we derived Kw for pure water. That doesn't mean I can never add acid to it or base to it. So what does happen if I add acid? Maybe I add HCl and I dissolve it in that pure water. What happens to the concentration of hydronium and hydroxide? Well, Kw can't change. That's describing the pure water that's still in there. But say I added an acid, so my concentration of hydronium goes up. The only way to keep that expression constant is hydroxide needs to decrease. And so I had a thought in my last lecture. I'm going to make a new figure on this. I think it might be helpful to see. It might seem like, well, that's kind of like magic, that hydronium goes up, hydroxide goes down, but Kw stays the same. It's actually Le Chatelier's principle, and it's because there's multiple equilibriums going on at the same time. So it's not as straightforward of just looking at one reaction. And they're two coupled reactions. So I don't want to get deep into that. Like I said, I'm going to make a new figure for that and let you guys see it so you can have a more intuitive understanding. But for right now, I would say use what I've just drawn there to say if I increase hydronium, right, because Kw is constant, that means the amount of hydroxide has to decrease. And that's what we're seeing down here in this figure. So we have our neutral solution, so pure water at 25 degrees C. Maybe I spike in some acid that increases the concentration of hydronium. By Kw, the concentration of hydroxide has to go down. And actually in such a way to keep Kw constant. That's why it goes down. And then we can also do the flip side as well, right? We could solve for the equation this way. Maybe I added some base. I dissolved some sodium hydroxide. The concentration of my hydroxide goes up. Therefore, hydronium must go down to keep Kw constant. That's what I see here. You started off neutral, and now add some hydroxide, so hydronium has to go down. So that's probably a more complicated slide. Well, it wasn't complicated, but kind of hammering it home. The reason for that is this equation we are seeing right here. I mean, they're all derived from the same equation, from this. We're going to use it a lot, and we're also going to use this equation to start deriving the pH scale. So I want to make sure we're comfortable with the idea of the equation. So are we good with that? Is there anything else that maybe I could clarify? All right. So what I have over here is the pH scale. And on the left-hand side of the figure, it has the concentration of hydronium. And then on the right-hand side of the figure, it has pH. So, right, here we are at neutral. What we said by definition at 25 degrees C, the concentration of hydronium, right, and that's why we're looking in yellow, hydronium, is 10 to the negative 7th molar. If I start adding more acid or something like that, something that makes more hydronium, well, the concentration of hydronium starts to increase, right? On the flip side, if I started adding something that added more base, right? And we saw that as base goes up, the hydroxide goes up, hydronium has to drop. And that's what we're seeing here. As it becomes more basic, the concentration of hydronium is dropping. And that agrees with everything we just saw on the last slide. What we see now, oh, maybe I should have made that yellow. Let me do that, keep things consistent. Okay. what we can also start to notice, there's a pattern here. Look at pH versus the exponent in the hydronium. If we were at a concentration of hydronium, which was 10 to the negative 11th, my pH is 11. 10 to the negative 10th, 10, 9, 8, 7. 10 to the negative 4th, it's 4, right? There's a relationship, exponential relationship between pH and how much hydronium there is around. And that's where the pH scale is going to be derived from. And so that's what we're going to do now. How can I go between pH, which is a measure of acidity, to concentration of hydronium? So first things, we just want to remind ourselves a couple of things. Basic pH, and this makes me feel, I've always felt was a little bit counterintuitive, but it actually makes sense mathematically, right? You would say, oh, usually, oh, making something more acidic, I'm adding more hydronium. Doesn't it mean I should be like, my pH should be going up? Yeah, it feels like it. The concentration is going up, but we're going to find out that actually the pH goes down. And there's a mathematical reason for that. But it's just something to get used to. It's almost like one of those things that's too easy that when you see it on a quiz, you kind of forget. So it's good to remind yourselves that acidic, low pH, basic, high pH. So what do I mean by pH? Where did this come from, right? So P is actually a function. It also stands for a phrase as well. I'll put that down. pH as a phrase literally means the power of hydrogen. That's how P was chosen as the sample. As the symbol, right? So it's the power of hydrogen. For us, we're going to think of it as a function, well, because it is, right? P for us will mean negative log. So therefore, pH, or the power, and power typically is talking about order of magnitude. So when you raise something to the power of, so it'd be the negative log of the concentration of hydronium. So maybe grab your calculator real quick if you got it, especially get it because I think on the next slide we have a practice problem to do. But let's do this. What if we took, let's find the pH when the concentration of hydronium is neutral, 10 to the negative 7th. So if I was going to write this in my calculator, I would say negative log 1 times 10 raised to the negative 7th, enter. So you're going to have practice on this too. So if you're not doing it along with me, that's fine. We'll do it on the next slide. And I get the number 7. And so that's what we're seeing here. So there is that relationship. I put my concentration of hydronium in, and then out pops my pH. Again, why things get smaller and why we have the negative sign here, right, is to make sure the pH numbers are positive numbers. That's why there's nothing special about the negative sign. It's just to make a pH a positive scale. That is all. One other thing that I want to drive, well, before I do that, fairly okay with that right now. That's our definition, and we're going to use it a lot. So if you're not comfortable, we will get comfortable. We'll do it enough. One thing I do want to point out, though, is specifically it is log, right? Everything that we've been doing for the most part has been natural log, ln, right? The difference is, right, take a look at your calculator. Log and ln are different. It's technically log base 10. In the United States, when you see log, it is implied to be log base 10. In other countries, that's not always the case, so you need to be careful with that sometimes. But in the United States, when you see log, it stands for log base 10. ln, which we use in the United States, is technically, you can write it as a log, but it's log base e. And so that means every 1 log unit change in the ln scale is going up by, the Euler's number. What is it? 2.1, I forget what it is, 2.7181 something, right? On the log scale, log base 10, every unit change of log goes up by a factor of 10, right? So actually, when we're looking here, the difference between, say, pure water and let's pick something like household ammonia, right? 7 to 12, that's 1, 2, 3, 4 orders of magnitude. That means it's 10,000 times more basic than pure water. And it sounds weird to say that, but as you start to deal with log scales, and this is why I say, like, when you guys do something, like if you make a mistake on a quiz or an exam and you're tenfold off or even 1,000-fold off, that I say that's better than being like some arbitrary number off, right? These giant fold changes, right? We just got to get used to that. And that's actually why we use the pH scale, because the changes are so giant. It makes it much easier to talk in smaller numbers, like 0 through 14, instead of 1 through 10 to the negative 14th, which is a huge scale. So I know I kind of just beat that to death, but I really do want to make sure we can see the distinct difference. So let me get through these slides, the stuff that I wrote out. One last thing I'll say on this, right, is what happens if I'm given the pH and I have to find the concentration of hydronium. Well, I've given you the equation here. I'm not going to give that to you on an equation sheet, but the process, the steps you take to derive, it's not really deriving the equation, it's rearranging it. If I start with the pH equation here, if I multiply both sides by -1, I get negative pH equals log concentration of hydronium. And then just like when we were doing with ln, right? When we would undo the natural log, we would exponentiate. So if this were ln, and this is incorrect, so don't write this down, but if we were doing ln, right? Just like when we were dealing, I think with it was the Clausius-Clapeyron equation, or when we were dealing with the Arrhenius equation, we've used the natural log a lot. However, we're no longer in base E. That means we're going to raise both sides, or exponentiate 10 raised to the power. So what that's going to do, I become 10 to the negative, whatever my pH value is, equals, and then just like when we were dealing with ln, the log just disappears, right? We exponentiated it. And so these two are exactly the same equations. I just wrote it in different order, that's all. So any questions on that? Basically, we have one new equation. I'd say these are our two take-home points. All set? All right. So what we're going to do is spend pretty much the rest of lecture just getting used to using these equations, right? So it's a pretty simple problem. And usually, like I say, I have you guys give me the givens and finds. I'll do that first, but I am going to let you do the math out yourself to get more comfortable doing this, right? So the problem says the hydrogen ion concentration for lemon juice is approximately that number. It says, what's the pH? So I'm not given too much information. Given I have a concentration, and I'll make the very reasonable assumption that when something says hydrogen ion concentration, which is common to say, we're talking directly about hydronium. And so we know our concentration is 0.0025. I'm being asked to find the pH of this solution. Right now, I pretty much only know two equations. One, I know the Kw expression. Right, and then I also have a new equation now of pH. So maybe you've already figured this out, but if not, you can give it a shot. So I'll give you maybe 30 seconds to give this problem a shot. 45 seconds, maybe. All right, it's been about 30 seconds. Does anyone have, so I can't see the participant window right now, but does anyone Want to jump in on this? What did they get for an answer? What's the pH?
I got 2.6.
I agree. So let me wipe this. I do agree it's 2.6. So I just want to show you real quick how you would do it. Hopefully everyone got to the same answer, right? If we know pH is equal to negative log of the concentration of hydronium, right? Should have recognized right off the bat that using the KW expression wasn't going to do us much because pH doesn't even show up in that expression. So we realized we should be using this expression. I'm solving for pH. All you need to do is plug into your calculator. Negative log of the concentration. So I'll do that on my calculator. I do negative log 0.0025. And I'm going to write out with incorrect sig fig. So I'm going to put a lot of numbers down. So I didn't get to see who was talking at that point, so forgive me if I forget who it was, but I was happy that you gave me 2.6 because it looks like two significant figures because my concentration is in two significant figures. So there's two little key points I want to bring up on this problem. One is log scale has new rules for sig fig. So I'm expected this number and actually use it kind of to like explain sig fig. So there's going to be a small sig fig change rule, and then one thing about units. So let me take care of the units first because we've actually done it before, and then I'll talk about sig fig. So the concentration of hydronium, right? We have the units in molarity, right? So when you're using this equation, you have to be in molar. You can't be in millimolar, micromolar. It has to be in molar because it's been derived from the KW expression, which is also in molar. The other thing is that we've seen this before with the natural log, right? We've said it kind of like makes the units disappear, right? So if you take the natural log or the log of a number with units, the resulting answer has always been unitless. And that's why when you do see here, there is no unit for pH, which is correct, right? So we're just going to have to keep in mind that that molarity goes away. We'll see in another example that when we do the reverse step, you're going to be, it's up to you to remember that the concentration has to be reported in molarity. There'll be no indication. So it's going to be something you just need to know, right? And again, it's based off of all the way back to the KW expression. My second point is on sig fig, and this is a little bit more weird. So if I took the concentration, the 0.0025 molar, and I put it into scientific notation, I could write that same number like this. And we see we have our two significant figures. And so if I was going to report my answer with two significant figures, I'd be 2.6. However, it actually is, and it's 2.60. And it looks like we gained significant figures, but we actually didn't. These two are significant. I'll explain in 2 seconds, right? These are significant, not significant, right? What this is like is take a look at our scientific notation. We don't count that -3 as a significant figure, right? It's just telling me where the decimal place goes. It's a placeholder. The same thing here. The 2 is a placeholder because it's on an order of magnitude scale. Like log, every time you go up by 1 log unit, you change by 10-fold. Every time you go up by an exponent by 1, 10 raised to the first, 10 raised to the second, right? Those are all 10-fold changes, so they're placeholders. So does that clear what I'm saying on that? The 2, like in our case here, any number before the decimal place is a placeholder. Anything after the decimal place on the log scale, those are significant. So we good with that? All right. So I'm glad we were able to do the math. So that's a good start. And then like I'm saying, I didn't expect anyone to get the sig fig stuff that's used as kind of a way to explain. Oh, I'm gonna skip through all my slides. There we go. All right, so again, hopefully you have your calculators with you. We'll do another problem. So it says acid rain is a matter of serious concern because most species of fish die in water having a pH lower than 4.5 to 5. So this is a kind of an old question that I wrote a while ago. Acid rain has become less of an issue in the last probably decade now, but it's still important, right? So acidification of riverways can kill fish, right? Probably extra information, but I think it has to deal with the ability for heme in the fish's gills in the blood to bind to oxygen, so the water in their blood, and they effectively suffocate. So having a low pH can kill fish. So let's take a look at the problem. A lot of information, but it's actually pretty simple. It just says calculate the concentration of hydronium in a lake that has a pH of 4.5. I'm going to drop you on the deep end on this one, but I'll give you a minute. See if you can calculate for me the concentration of hydronium just given the pH of 4.5. All right, about 15 more seconds, and then I'm going to ask someone to offer up a solution. All right, does anyone want to jump on this problem? What did someone get for an answer? All right, how about, let's do this. So Aspen, any idea? Get a shot for that one?
I got 3.2 times 10 to the negative fifth.
I like it. So let me write that down. I just want to do out the math. So that's good. I'm glad. That's 2 classes in a row. I've had everyone get it right on the first shot. The only thing I'm going to disagree with is actually the number of sig fig, which is totally fine. We literally learned it 4 minutes ago, right? So let's talk a little bit about that. First, I just want to do quickly, because you got it right, I'm just going to write out how to solve for it, and then we'll talk again about sig fig. So we recognize, we're going to use the pH expression. And this time, instead of being given hydronium, I've been given pH. So I have my 4.5. And so just like when I was deriving that other equation, I said it makes your life so much easier to put the negative sign over first. Then we exponentiate. And we're left with this. It looks like that equal sign's too high. This is technically going to be incorrect if you report this number, because I've never met a person in my life that has found it intuitive to report things, the order of magnitude as a fraction or a decimal. Because it's one thing, I intuitively understand what 10 to the negative fourth is, right? I know it's small and it's 0.0001. 10 to the negative 4.5, I have absolutely no clue how small it is or what it even insinuates, right? So to be fully correct, you do need to do that one extra step and exponentiate. So 10 raised to the negative 4.5. The concentration of hydronium is equal to 3. I'm just going to include a bunch of extra sig fig, right? Or maybe give myself more space. The concentration of hydronium, 3.16 times 10 to the negative fifth, right? And so 2 things on this. So I agree with how it was solved. I know I didn't ask for it specifically, and I know it's difficult over online, but we got to remember we want to include our units of molar, right? Because Again, we don't see anywhere in this problem that molarity or molar was mentioned, but it's up to us to recognize that the concentration of hydronium using this equation has to be molar. Again, because it was derived from the Kw expression. If we're talking about significant figures, though, I would report this with correct sig fig to 3 times 10 to the negative 5th molar. And the reason for that, right, and this is just going to come with practice. When I look at 4.5, right, the 4 is the placeholder. It's telling me what order of magnitude. That means I have 1 sig fig from that 5. And so when I report my answer, I also want to have 1 sig fig as well. So any clarification on this particular problem? All right, sounds like we're in good shape. So this one is a little bit more tricky. So what I'm gonna do is I'll help you set up, actually, you know what? I'm gonna have you guys do this one. This one's a little bit more tricky. Set up your givens and finds. I'm gonna give you the heads up. Start with this equation though. So let's read through it. It says calculate the pH of an aqueous ammonia solution that has a hydroxide concentration of that. Now I want you to find the pH. So I'm going to give you a full minute, maybe a minute and change, to work on this. And while you do that, I'm just going to start organizing my work here. So we're about a minute in. I'll give you about 20 more seconds-ish if you haven't finished it off. All right. Does anyone have a pH for me? I'm not so worried. So, you know, try to work on the sig fig, but I'm more care about could you get to even a number for pH?
I don't know if this is right, but I got 11.28.
Yep. I forgot what the decimal is because I have to do it up myself because it's not on the screen. But yeah, it's definitely the pH 11 point something. So yeah, you've probably done it right. That's a great sign. So for anyone who maybe was struggling with that, or maybe everyone did great, I don't know, but just for the record, right? Some of these problems, a lot of it's going to be, we have a lot of equations we can use, and there's multiple ways to solve these types of problems. So we need to be pretty comfortable reaching into our tool bag with different equations and starting to say, hey, what do I have? Can I make a path to where I'm going? So if I look at what I have, all I have is the concentration of hydroxide. So I need to set up some sort of path to get to pH. Well, my path could be, well, I have one equation, effectively one unknown. That's that hydronium. I can dump it into that equation, and then out pops pH. So it's actually gonna be a two-step process this time. So I'll just do it slowly on the screen, right? So if I plug in my numbers, if I'm solving with 0.1 times 10 to the negative 14th equals my unknown, which is hydronium concentration, multiplied by 0.0019 molar. Right, and again, this is where I think units get a little bit wonky because it's not going to be per molar now for hydronium. So it's more, let's just know what those brackets mean. They mean molarity. So this will be 1.0 times 10 to the negative 14th keep losing that 1. I don't know why. Divided by 0.0019. If we do that out, 1 times 10 raised to the negative 14th divided by 0.0019, we get 5.263, blah, 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 10 to the negative 12. That'll be in molar. We're not quite done yet, right? Because the problem was asking us to calculate pH. So now I know I can just take the negative log of 5.263 times 10 to the negative 12th. Take the negative log of the number, 11.28. So I couldn't see who was talking before. I think you had also said 0.28. So we're in good shape. And I like why we also went to 11.28. I have 2 significant figures in the only information that I was given, plus KW has 2 significant figures. That means my final answer needs to have 2 significant figures in the decimal place. Again, that 11 to the left of the decimal place, right? That is my placeholder. So we're in good shape. We didn't gain sig fig. We just have to follow new rules. So let me just do a time check. All right. So actually, this is just, yeah, let's skip through these slides because this is going to be up on YouTube, so you can still see a lower, way to do it. So we got our 11. Oh, I think I messed up the number. Oh, because I rounded. Shouldn't have rounded on the slides. What I did by hand was actually more correct, where I didn't round into the last step. So lesson learned. All right. So we have 3 more minutes, but that's not going to be enough to start the next problem. So we should end here, but we have 3 minutes. If you have any questions that I can take care of, I'll be more than happy to. If you're all set, then feel free to log off. And I'll see you all on Friday.
Do you by any chance know when the next quiz will be?